Well, thanks very much for the introduction, and thank you to all of the organizers for the opportunity to speak here. So I will talk about differential aspects of p-adic moduli spaces. Much of what I say will be in this paper if you're curious, but I will also say some things that are not in that paper. Unfortunately, I have to leave after this session, so after tonight, so I won't see the talks tomorrow. But I mean, all of the talks will be great, and I know people are tired. All the talks have been great, and I'm sure the ones tomorrow will be, but people are tired. You're already starting to think and dream about what you're going to do over the weekend in sunny Marseille or wherever you'll be. And so I just have one piece of advice to give you as you enter into your fun, sunny weekend, which is you should wear p-adic sunscreen. So I don't know if you guys have heard about this stuff. It's really cool. It's called BC of 1/2. And so it lives inside of CP squared, so there's two-dimensional space over CP. But it's kind of like, has this amazing property where if you draw any line inside of CP squared, well, actually, if you take that line and you intersect it with this BC1 of 1/2 inside of here, you're going to find a QP squared worth of points. So that's lines going some way, but this applies like for any line. You can sort of do any direction you want. All these lines will have, so this locally profinite. So for any CP line, L and CP squared, the intersection of L with BC 1/2, you can sort of identify it with a translit of some QP squared, so some two-dimensional QP subspace of, and CP is an infinite dimensional of a QP vector space, and you can identify with a translit of a two-dimensional subspace in there. So what that means is if you go out in the sun and you sort of cover yourself with a nice layer of BC 1/2, I mean, it's pretty close to just being CP. You're going to barely notice putting it on. But then no matter sort of what direction the p-adic sun's rays are coming in at you, they're going to be blocked by sort of like an enormous profinite set of points. So this has like SPF like 1 over p to 1,000. 1 over p to 1,000, which is really big in sort of p-adic numbers. So this is good p-adic sunscreen. But alas, there's a problem. So this is a math conference, and this is actually only a mathematical solution to p-adic sunburn. It's not really an engineering solution. And of course, the reason being that if you are outside as a human being on some p-adic planet, when the planet itself is affecting the curvature of the light rays coming in. I mean, this is general relativity. So as you sort of stand outside, the light is not going to come in along these straight lines and hit you. It's going to sort of curve a little bit. So here's the sun, your p-adic planet. Maybe there's even a black hole up here to really sort of exaggerate the picture. So you have these light rays sort of curving in to hit you. And so before we can bring this product to market, we're going to need to address something I'd like to call the relativistic p-adic sunscreen conjecture. And so what does this say? So let me just give sort of a simple case. So the conjecture is, let me do the simplest possible case. There are infinitely many solutions to y squared is equal to x inside of BC 1/2. So this is sort of, right, of course there's plenty of solutions to y squared equals x inside of CP squared. BC of 1/2 sort of sits inside of here. And so you can ask, like, are there sort of infinitely many solutions? Well, the origin is one solution. So you've got at least one. And then the question is sort of, are there more solutions than that? And so, well, as with all problems involving general relativity. In order to think about this, you need to sort of introduce some new tools from differential geometry to sort of think about this. And so let me sort of give it like a differential geometry perspective on why this is like a reasonable conjecture. There are many reasons now for which you might almost believe, and I'll go into some of them in more detail later, but there are sort of maybe a reasonable reason to believe that this BC 1.5 living inside of here, I mean, that it sort of behaves like a manifold inside of CP squared. It's not a one-dimensional manifold. It's a little bit bigger than one-dimensional because somehow it sort of has sort of two QP dimensions on top of each CP dimension, and that's sort of why you have those sort of, oops. Oh, I'm not supposed to throw that up. So that, yes? Yes? Yeah, I mean, I guess that's also as bad as throwing it up. Yeah, I mean, it's bad. I don't think it's appropriate for this venue. I hope you won't experience it. Okay, so yeah.
The inclusion here, I'm guessing, must be like a quasi-logarithm.
Yeah, that's right. Yeah.
But then the target of that's not a ring. I mean, your CP squared, you can
But
make it a ring, I suppose. Do you just mean the product ring?
Well, I mean, like this is a curve inside of two-dimensional space. And I'm just taking the intersection. Yeah.
Okay.
Yeah, and then you're right. This is a quasi-logarithm map, and maybe I should have said. I mean, so this p-adic sunscreen property I wrote up there, that for any CP line it intersects at sort of all these points. That's just a reformulation of the surjectivity of the Gross-Hopkins period map. So that's a good exercise to think about. Okay, yeah, so this BC 1/2, it lives inside of CP squared, and it's sort of reasonable to think that it's a manifold. And it's also sort of a vector subspace. And so if I look at like the tangent space of BC 1/2 sort of at 0, it's, well, it should just be BC 1/2 again. I mean, if I have some vector, some group object, some vector space object, and I sort of look at its tangent space at 0, like it's sort of just going to be that thing again. That would certainly be true like if I took like a CP line. And then, well, let me call this curve C. Now if I sort of take the tangent space to C at 0, well, that's just, okay, this curve sort of is a parabola, so like goes like that. Y squared is equal, like this. So I guess this is spanned by E2. So it's sort of like just like a vertical line. Then you ask, well, both these, so this curve and sort of this other weird submanifold, they both contain this point 0. And so I want to know, like, well, maybe like is the intersection transverse at that point? And so I want to know, like, well, do these do these points, like do these tangent spaces together, do they span all of CP squared? And it's true, sort of like if I take these together, then I really get CP squared. So you can sort of think of that from this p-adic sunscreen property. I mean, sort of if I take any sort of line sort of horizontal to E2, then I have sort of QP points in it. As I have BC 1/2 points in it. So you can sort of think about this. So you really, so this intersection is transverse. Okay, and then, well, I have a transverse intersection, so I go back to sort of my regular manifolds class, and I say, well, if I have a transverse intersection of two manifolds, then sort of in some neighborhood of that intersection, it should also be a manifold. And how do I figure out what that manifold looks like? Well, I should say what is the tangent space of the intersection of the intersection? It's just the intersection of those two tangent spaces. So the tangent space of, so maybe I'll call the I is the intersection. So the tangent space of the intersection I at this point, at this origin, well, it's just now the intersection of sort of BC 1/2 with this line spanned by E2. And again, the p-adic sunscreen property tells me, and the p-adic sunscreen sort of property is a linear property, and so it tells me that this is sort of QP squared. So this is not the QP squared inside of CP squared, but sort of a two-dimensional sort of QP subspace. Sorry, let me say a two-dimensional QP subspace. Okay. Yes, I'll give. It is possible. I will even do it in a second, but I sort of just want to sort of say this first. So you have this two-dimensional QP subspace, and then you should expect, like maybe locally around this intersection point, this looks like a two-dimensional sort of QP analytic manifold. So sort of this conjecture is sort of weaker than saying that. I'm just saying maybe this reflects enough of the geometry to say that there are actually like infinitely many solutions to this equation. So let me sort of make this more explicit, like what it means to sort of solve this equation. So BC of 1/2, I mean, there are many ways I can think of it. I can think of it as global sections of a sort of vector bundle O of 1/2 on the Fargues-Fontaine curve. I could think of it as being sort of the universal cover, like the points of the universal cover of a Lubin-Tate formal group for a degree 2 extension of E, but probably of QP. But the simplest thing to say is if I take Fontaine's crystalline period ring and I take the things inside of it where the Frobenius operator on that squares to P. So this is a phi. Sorry, my phis look like p's. But that says phi squared is equal to P. That's BC of 1/2. And so then what does it mean to sort of solve this equation? You want let's say a little b inside of this phi squared equals P part of the crystalline period ring, such that if I look at, so what does this map? You send it sort of, you send it to theta of B. So theta is sort of the map from B plus Chris to CP. So it's Fontaine's sort of usual map. You send it to theta of B, and then you sort of send it to theta of phi of B. Apply the Frobenius and then send it to theta. And so you're sort of looking for some B such that the theta of B and theta of the Frobenius applied to B sort of satisfy this relation where 1 squared is equal to x. Okay? And so if you can solve that, and moreover you can solve that sort of kind of equation for any sort of like analytic germ through the origin, then this p-adic sunscreen really sort of will be effective in the real world too, and then we can go ahead and start selling it. And in the US, that will replace the National Science Foundation, I think. But okay. And I don't know the answer to this conjecture. I thought about it a little bit, and I mean, I find it sort of difficult to make these kinds of computations in this period ring. Pierre once told me he thinks it can be done, but he told me he thinks the computation can be made. But do you still stand by that? Sorry, I didn't tell him I was going to ask him about it. But anyway, I actually don't. I say this is a conjecture in the positive because I'm an optimist. It's not clear to me really whether it's reasonable to expect there to be solutions or not. I mean, I think this is like a good question that would really tell us something new if you were able to answer it. And so because of that, I've given it a name that will look really cool on your resume if you solve it. And I will put a little PDF on my website with this p-adic sunscreen conjecture. So then if you prove this, you can sort of then cite that you proved some conjecture. And on top of that, this property of these intersecting lines, it kind of reminds me of like this cool thing in fractal geometry where you sort of like in R2 you can sort of like if in R2 or sort of R3 like you up to measure 0 you can sort of choose sets that project however you want onto things, and so this is a result of Falconer, and sort of people have used this result to sort of build actual digital sundials. And so if you solve this conjecture or resolve this conjecture one way or the other, I will also buy you a digital sundial. So this is sort of the full suite of rewards you get. Okay, so the rest of the talk won't be as funny. But and like this is basically the kind of thing I want to talk about today. Is it sort of turns out there's sort of a framework. Yeah, I mean, like anything smooth through zero should intersect this. I mean, somehow. So like if you believe this manifold logic, anything sort of smooth passing through zero should intersect this infinitely many times. So, I mean.
Oh, do you even think that the intersection should be dense around the origin?
Yeah, that's right. I mean, I think it should look like sort of QP squared around the origin, but that's the optimistic answer. I mean, it's sort of it might be a stretch. I don't know. Right, but so this is sort of illustrating a more general thing. So in some recent work, I introduced sort of some notion called inscribed V-sheaves that's somehow very closely related actually to this analytic prismatization stuff. And it's related in the sense that both theories are sort of things that in particular, like, they address some defect with perfectoid spaces. So like in p-adic geometry has been using perfectoid spaces for a while now, especially to sort of like the perfectoid spaces are good for like topological properties, but somehow you sort of lose something by not having sort of a nilpotence or sort of like these dagger nilpotents. You lose sort of like differential aspects of the theory. And so both of these things correct that. So the setup I use is. I mean, maybe simpler in some sense and sort of more adapted to sort of, in particular, like actually making computations of this kind. So computing tangent bundles. So this gives sort of a good theory for differential computations. I mean, sort of with, and especially sort of p-adic moduli spaces that sort of like maybe don't exist in sort of another world where you know how to make differential computations. Like if something is just a perfectoid space, there's not much you can do with it differentially. If something's just a diamond, somehow this is even worse. Okay, but somehow like I mean, this is all of these computations in that world. And they're based on some type of nilpotent structure. I mean, yeah, like it's like scheme theory. I mean, sort of like you can have a tangent space even if you're just a point because you might have nilpotence involved, and so like the same thing is here, and so it's this theory like it produces sort of lots of like very nice computations that sort of somehow contain a lot of information. But maybe the overall question in sort of this talk is like, do they actually contain like actual geometric information? I mean, so somehow like right, this conference is on geometrization of the Langlands program, and like some of the talks forgot the geometry part, and this talk maybe unfortunately like all the talks have been great. Like that's not an insult. It's just my excuse because I sort of forgot the Langlands part in my talk. So I want to sort of talk more about like the actual geometry of things. And so yeah, okay. So what do I want to do? I want to sort of, well, one, give more examples relevant to sort of like Fargues Scholze. Then two, I will say something about what the actual definition and sort of like underlying theory is. And then lastly, I want to sort of and connect this to analytic prismatization and sort of just explain sort of how it fits in with some of the things that have already been discussed to some degree or another this week. So that's sort of where I'm going. So some people don't like when you sort of give examples of things before giving the actual definition of the thing you're like computing. Let me sort of give my excuse for why I'm doing that. And some of the, like the reason is the examples I'll give, like you can actually, you can sort of, like you can actually understand them sort of geometrically, and you can sort of do like some basic geometric reasoning to figure out what the answer should be, and then you can sort of check afterwards with the theory that this is actually the right thing. And I think that's somehow like important to see if you want to sort of do something, like, I don't know, if you're interested in using this theory for something. And then I'll be brief about the definitions, because somehow, like, I mean, in the end, probably most of what I do should be somehow subsumed in the same kind of formalism that is used for analytic prismatization, and you want to think of these computations I'm making as sort of reflecting some structure in that world, and then that sort of maybe is one avenue you can pursue to sort of try and actually like prove more things using these computations that we'll talk about. Right. Are there any questions while I move the boards around? Excellent.
I thought for sure you'd make a formal scheme joke.
Formal scheme joke. I don't get it. It was
Well, in BC, it is kind of representable by a formal scheme. So
Yeah.
it is SPF.
Oh man, that's so good. Wow. Jared, get back up here. You finish. But I told some people that I'd finished preparing my jokes like this afternoon, and I think I finished too soon. It was, Okay, so let me look at a projective line over CP. So this space can be decomposed. It sort of has a nice stratification. One part of this stratification is the QP points of the projective line. The other part of the stratification is, well, just their complement, which is the Drinfeld upper half plane. And it's really sort of just an open subset of P1 of CP. Okay, and so this is a special case of the Newton stratification that sort of exists in all flag for sort of all flag varieties in p-adic geometry, and sort of generalizations to sort of like these Schubert cells and moduli of mixed characteristic, or and sort of these Schubert cells in the affine Grassmannian. And so like the stratification comes from sort of you take a trivial bundle and sort of you use the data of a filtration or sort of a lattice, and in the more general case, to make some modification on the Fargue-Fontaine curve, and that sort of produces some new vector bundle, and then you stratify it based on like the isomorphism class of that vector bundle that you get. That doesn't really matter for what I'm going to do. I'm just going to tell you sort of something about these strata in some cases. And so first case is P1 of CP. And what I want to point out about this is like both parts of the strata are sort of like very analytic in nature. They just sort of live in two different worlds somehow. So this is rigid analytic variety over CP. This P1 of QP, I mean, you could think of it as a diamond, but then you'd sort of lose, or a perfectoid space, but then you sort of lose its analytic structure. But I mean, like, you sort of would only think about this as a perfectoid space if you knew too much. I mean, if you were just sort of being young and bright-eyed about it, you would say this is just like a QP analytic manifold. Okay, and so like the tangent spaces like if I take the tangent space for a P1 of QP at any point x in it, then I really should just get a one-dimensional QP vector space. And if I took sort of the this rigid variety over CP, so I took this Drinfeld upper half plane, you know that's a CP vector space. But some of these, like, these are really different things in terms of what you can do with them. So if I have a tangent vector over here, I mean, I could sort of differentiate sort of like analytic functions valued in QP. I could differentiate analytic functions valued in CP. I could differentiate analytic functions valued in like B plus de Rham, or like O of yi if you know some more exotic period rings. I mean, you can differentiate sort of pretty much like any type of analytic function on this guy, and there are a lot like there are interesting analytic functions with all of these period rings. Over here, when I just look at this rigid line variety, and the only sort of functions on that sort of are CP functions. Like there's no like B plus de Rham mod t squared functions on this thing. So somehow like in p-adic Hodge tree, you have all these different rings you could take your functions on, but like you're never going to see interesting ones except sort of CP valued functions here, and then you have these sort of analytic ones. And like even like somehow like if you could see other functions, you would never be able to differentiate them along these like CP vector fields because some of these never split. So somehow there's something interesting happening about sort of the relation of these things, but these are both really sort of like things you can sort of think about classically in analytic geometry without sort of doing anything too complicated. So let's move on to P2 of CP. Okay. So now this has a similar kind of Newton stratification. So you still have your P2 of QP, and then you still have your P2 of CP minus, but now sort of when you take the top strata, you don't just remove sort of all of the QP points, so you don't remove all of the lines over QP, you remove any line that sort of is contained in a plane defined over QP. So this is lines in a plane over QP. Okay, and so then what's in this middle part? Well, you just have, let me just call it X. And so this is sort of, you have QP lines that are, so you have lines that are contained in a, like you have CP lines that are contained in a QP plane, but only one of them. They're not sort of contained in two QP planes, because then they would just be a QP line. So you sort of throw out these QP lines. Okay, so let's draw a picture of that guy. So here's sort of like three-dimensional space over CP. And then so you can draw some QP points in sort of CP cubed, and then so like what is sort of a plane that's defined over QP? It's sort of like I would sort of pick some of these points and I would sort of draw like the plane between them. Okay, so I shouldn't really fill that in. Like, so this is sort of a plane over QP squared. So this is QP squared, a copy of QP squared inside of CP cubed. And then then finally I have sort of also just maybe I'll even use one more color. I have also some line inside of this plane. So this is CP. And so this plane, well, it's QP squared, but obviously this CP line is not inside of QP squared. It's sort of in sort of this QP squared sort of tensor CP. So I take this plane over QP, but then I sort of view it as plane over CP, and I have CP line inside of it. Okay. And so then let's compute. Oh, I learned how to draw this picture from my advisor, by the way. It's, okay, good. So what are the tangent spaces? Like this thing is sort of a QP analytic manifold, and so this tangent space is like any tangent space is just a QP squared here. This guy is a two-dimensional rigid analytic variety, so any tangent space is a CP squared here. And then we're left with this sort of interesting guy X in the middle. But you just look at this picture and you sort of know what its tangent spaces are, because how do you move around inside of this moduli space? Well, I have two options. Like I can move my CP line inside of my plane. So that gives me one CP dimension, one sort of CP degree of freedom. Or I could sort of move around my, my plane inside of CP cubed. So that sort of gives me planes inside of CP. That gives me like I think I have 1 degree of freedom, 1 CP degree of freedom, sorry, one QP degree of freedom moving around my plane, and 1 sort of CP degree of freedom moving around my line. So you see that the tangent space here is, at any point, is going to be sort of QP plus CP. But somehow, and like this is like really like homogeneous. I'm sorry, the reason sort of this analysis was correct is because somehow like, if I move the plane, I have to move the line too, because otherwise I would sort of be in this strata. If I sort of, okay, so I mean, like this is sort of like somehow like even like really like a homogeneous space like for this kind of structure. Like it really like locally looks like just like QP. Like the space locally looks like QP times CP. So this sort of has some type of manifold structure on it. Okay, but it doesn't sort of fit so cleanly in sort of the worlds we know, right? Because I can't sort of think of it as a QP analytic manifold, but I can't think of it as a rigid analytic variety. I can think of it as a diamond, but I mean sort of, okay, but it actually sort of has sort of interesting, has some interesting like QP analytic functions on it, and it sort of something like purely CP analytic functions on it too. And you want to sort of try and understand how you can differentiate those along these fields, and so you need some sort of like mixed theory here. What do I have up here? Okay, so I'm going to do like one last like example just to illustrate that this can get much more complicated, and then it's sort of with the kinds of arguments I've made so far, it's not so clear what's going on, but there are extensions of this kind of reasoning. So for my last example of sort of a Newton stratification, I want to look at the Grassmannian of two-dimensional planes inside of five-dimensional space. And I want to look at sort of the Newton strata corresponding to sort of like the slopes 1/3 and 1/2. So if you know what that means, great. Otherwise, don't worry about it. This is just some way of indexing these strata in this case. And so this you have some strata here. And okay, now I need to go to my notes to see what this looks like. Right, right, you're saying like the tangent. So X is the Newton strata associated to B. Okay, and so what is the tangent space going to be at sort of some point? Well, let me tell you some things about it. It's going to be contained in 6-dimensional space because this is sort of has 6 dimensions, so it's going to be contained in sort of the tangent space of this thing at any point. It has, I can tell you what its dimension is. The dimension is 5, 6. So what does that mean? That means it has 5 CP dimensions and 6 QP dimensions. But the thing is that so it turns out in these tangent spaces, like they're always Banach-Holmez spaces. So this is sort of some category of vector spaces that was introduced by Banach, I believe. It's some category of vector spaces that mixes sort of finite dimensional QP vector spaces and finite dimensional CP vector spaces, and sort of it especially includes like the kinds of ones that arise sort of out of period rings constructions. And so like this is sort of Banach-Colmez space. And like in like these low dimensional examples, sort of like there's not many options for like a 1-1 Banach-Colmez space. And so you got this like QP plus CP. And in fact, like if you go up just like and do PNs, sort of like you'll always get things that are just like some copies of QP and some copies of CP. But here it sort of can be more complicated. I mean, sort of just pinning down these two numbers sort of doesn't sort of tell you sort of exactly what this is usually. I can tell you sort of something else. So I can tell you the normal bundle is just BC of, well, okay, so something called sort of BC of minus 1/6. So this is a Banach-Colmez space. So this has dimension QP dimension, so CP dimension 1, and then QP dimension minus 6. So that's sort of the kind of thing that can happen with Banach-Colmez spaces. Is your sort of one part of your QP part of the dimension can be negative. I mean, you already sort of would see that like in sort of this example. Like if I sort of try to compute the normal bundle sort of this stratum where my tangent space is QP and CP, well, I'd be taking CP squared mod QP plus CP. So like the CP mod CP, that would give me 0, but then I have a CP mod QP left. And so that's sort of a 1 CP dimension, but minus 1 QP dimension. That can sort of happen there. Good, and so, I don't know what it is, and I don't know if it's independent of X, but I can sort of, well, I'm not going to, but I could. There is a sort of explicit presentation of this guy as quotient of what is this? So you have a 625 by a so a 625 by a I could figure it out, but let me just so by a 119. No, that doesn't make any sense. What did I write down? Well, as a quotient of a. Oh yeah, no, sorry, 5, 6. Yeah, okay. Sorry, I was looking at the wrong number. Okay. 6 minus 1 is 5. 25 minus 19 is 6. They always say you should include one proof in a talk, so there you go. You have this explicit presentation, and where is this coming from? So this 119 is actually really simple. So you take your B, and this formula, this formula works in general. Like you always sort of get such a presentation for any Newton stratum, and so you can sort of say lots of things about it. And so you take your B, and then you look at sort of like the isocrystal coming from the adjoint representation on the Lie algebra of G. And then that sort of gives you some vector bundle on the Fargues-Fontaine curve. And you take the global sections of that, and that sort of gives you this space. So if you do that in this case, you get sort of, if you do that in this case, you get sort of this like 119. And then this 625, well, it's a little bit more complicated. Like, but you can sort of, there are ways to understand it. But it actually already sort of in some sense showed up in Jared's talk. So like Jared was talking about sort of like these infinite level moduli, like local Shimura varieties. More generally, you have like infinite level like moduli of modifications. And this is sort of actually a tangent space of one of those infinite level moduli of modifications. Now, sort of the interesting thing is we know, and due to computations already, sort of going back to Jared and then Alexander Ivanov, who's also here, that's like the tangent spaces of these infinite level Shimura varieties. Like they're not sort of locally constant, and they're not constant. I mean, somehow like there's some open locus where they're all the same, but they can sort of change from point to point. And so somehow like this guy, like the thing that has this tangent space like has no hope of really having like a homogeneous Banach-Colmez structure. But that doesn't exclude, and this one really does on the other hand. But in the quotient, it doesn't really exclude that the quotient couldn't be always the same. In fact, like in these other examples we saw, like the quotient really didn't depend on the point you took. And so let me just like that. I think this is a really interesting open question. So let me just leave that as a question. So is the isomorphism class of sort of this tangent bundle to this Newton strata, independent of x? So what I mean is sort of like at every geometric point, I get some tangent space. It's a Bonnet-Clomez space, has some sort of explicit presentation, and it is explicit once you know where it comes from. And then you want to know, is the thing really independent of x? And so if so, then you might sort of actually hope that like this Newton stratum, which a priori, okay, you guys are all, there are a lot of young faces in the audience, so like there are probably people here who like don't realize like how mysterious this stuff all was, like even like 15 years ago. I remember like, David Hansen coming to Chicago and like while I was a graduate student, and like giving a talk about, and maybe it was even joint work with Jared. But they were just like investigating the diamond structure, and this is like saying that this result, like you have like these Newton strata are locally closed subdiamonds. This was like, and like this was kind of like an incredible thing at the time when sort of people were putting this together. And then just like before that, I think we just like didn't even know how to understand them at all, or not long before that, we didn't even really know that they existed. So this is saying like there's actually the possibility like not only do these Newton strata like exist and sort of like, but like at least in the examples I know how to compute, like they actually look like they probably could be like just like actually locally like Bonnet-Clomez spaces. Like they could really be homogeneous spaces. Again, like I think someone like, yeah, it would be interesting to know one way or other. And then like this is in the spirit of sort of the relativistic p-adic sunscreen conjecture. But sort of maybe a little bit more like immediately applicable. I think you would really learn something interesting if you understood like, do these tangent bundle computations, do they tell you something about the geometry, or is it sort of really purely nilpotent information you're getting? In particular, if you knew that sort of these were really like locally like a Bonnet-Clomez space in some way, then you could sort of like try and like set up sort of, I don't know, like interesting theories of like D modules on these things where you really had like sheaves of differential operators, but sort of valued in sort of some exotic period rings for functions. And you could like, but maybe these are somehow encoded in analytic prismatization already, but some of this would give you like, I don't know, like it's something like actually like really you could get your hands on to work with. And I think it would sort of be extremely interesting, like from a geometric representation theory perspective, to like try and understand sort of this kind of D module structure. So this is like, and this is how I make contact with something related to representation theory in this talk, because I say that sentence. Okay, so that's my example. Maybe I'll say. So like when you actually carry out this computation, like basically like you do a bunch of things involving like homogeneous spaces. So okay, that'll work. So you look at homogeneous spaces for like you have some group G floating around, like GL6, for example, and you look at sort of some homogeneous spaces, but now like where your homogeneous spaces sort of are. Sorry, I'm not very good at doing two things at once. Left below. Left. Thank you. And so you have the, okay. So like you make these computations like all using homogeneous spaces, but like you have homogeneous spaces for like B to ROM and B plus to ROM, like the G points of B plus to ROM and G points of B to ROM and the G points of like this like ring BE that you get when you sort of delete this sort of point on the period. But in the end, like once you get over the fact that you're sort of doing like these weird homogeneous spaces, like the computation, like you can do these computations just like pretending you're doing differential geometry. This is sort of kind of the point, and it really is some geometric structure in the strong sense of, in the strong classical sense of geometric, let's say. And there are some other interesting things I want to say about these examples, so maybe I'll just say them out loud. So another thing is that you can also do this over the complex numbers. And it sort of encodes some interesting information that's maybe easier to describe than sort of in the p-adic setting. Like over the complex number, you have this theory of period domains in complex Hodge theory, and they come from, like, you want to understand like the families of Hodge structures coming from cohomology of varieties, and when you look at these period domains, you have a constraint called Griffith's transversality on sort of the kind of things that can be like an image of a period map. So there's sort of a nice way you can encode this in sort of some complex analog of this theory, which is you look at sort of, you sort of replace the world of complex manifolds with the world of like C double brackets T manifolds. So like a simple way you could mean that is like a complex manifold is an almost complex manifold. So it's a real manifold with like an I on its tangent bundle. And instead of taking just like an I that squares to -1 on the tangent bundle, you also give yourself a T that acts by sort of some nilpotent endomorphism of the tangent bundle. You get something called a C double brackets T manifold. And then you can sort of like characterize this Griffith's transversality condition on sort of on like Griffith's on sort of subsets of a flag variety, but by saying those are sort of this flag variety actually embeds sort of the complex manifold naturally in sort of a Schubert cell in an affine Grassmannian. The Schubert cell has like a C double brackets T manifold structure on it, and if you sort of ask like when does sort of like that agree with the sort of trivial C double brackets T manifold structure on like a submanifold of flag variety, sort of exactly equivalent to this Griffith's transversality condition. Okay, so like, and then you can also define these Newton strata for like Schubert cells and Grassmannians over the complex numbers, and there maybe like you have some ideas for like how you would start sort of trying to sort of treat differential operators in that setting, and similarly, and like there you would get sort of like some almost twister structure instead of like a C double brackets T almost structure. So okay, like just as for another way to think about these things. Good. So I said I'd say something about definitions, and I said I'd say something about analytic prismatization. Let me do definitions. I forgot, I am allowed to use these boards, right? This is good, okay. Well, it's never too late. So right, in all of these computations in the p-adic setting that I said, and they all sort of can be made completely precise and are made completely precise in sort of this paper I mentioned, using sort of this theory of inscribed V-sheaves. And so, well, in the theory of V-sheaves, your test objects are perfectoid spaces. And in the theory of inscribed V-sheaves, you sort of just like give yourself a little bit of extra nilpotent structure to work with. So the test objects are, you have P, a perfectoid space, and characteristic P, or perfectoid. And then, well, when you take that perfectoid space, you have an associated Fargue-Fontaine curve we've seen a few times this week. And then you can look at sort of a nilpotent thickening of it. We've also seen nilpotent thickenings of the Fargue-Fontaine curve this week. So they had these sort of, in like Artier and Johannes' talks, you had these sort of thickenings you got by sort of taking this like nil perfectoid thing and stitching it in at a closed point. And so like sort of they had sort of, yeah, let me draw a picture. They were using sort of these pictures, these thickenings, like you just sort of pick one point on your curve and you thicken at that point. And I want to use thickenings that sort of are actually sort of flat. So I want to use thickenings that look like this. And let me use like not the actual definition I give, but let me use something even simpler. So let me just take x of the form, I take my Fargue-Fontaine curve, and then I sort of base change from QP to SPA A, where A over QP is Artinian, and the residue fields or the reduction is just QP. This is like the simplest kind of thickening I could do. I could just take a thickening over QP and base change it to here. Okay, so that's, these are sort of the test objects I want to use. Right, and so like of course, like if you have a V-sheaf, like instead of thinking of evaluating it on a perfectoid space, you could think you're evaluating it on the associated Fargue-Fontaine curve. And then sort of, yeah? Yeah, for the moment, yes. But right now, and like the point, I mean, so there are many different choices of test categories you could work with. If you only want to make differential computations, this is basically all you need. In my paper, I would sort of work with more, but probably like one should actually work with even more, like in sort of analytic precipitation. But somehow like this, I don't have much time, so these are all the ones I want right now, because this is enough to sort of make all the differential computations. Okay, and then sort of so an inscribed V-sheaf. Okay, well, so in this category of test objects is sort of fibered over perfectoid spaces. So I just pull back the sort of topology from perfectoid spaces when I talk about V-sheaves. So that means sort of really I'm not allowed to sort of like localize at all sort of like on the curve itself. Like I'm sort of only allowed to sort of change the base, the perfectoid space. So inscribed V-sheaves, they're sort of V-sheaves on this category such that, so it's a V-sheaf, call it script S, such that if I have like a thickening, and I sort of take a push out with another thickening, then I get just the product of those two things. Okay, so this is sort of the definition of inscribed V-sheaf. And so when you have an inscribed V-sheaf, like there are two things you can do with it. Like one, you could take its underlying V-sheaf by sort of just like only evaluating on sort of like Fargue-Fontaine curves themselves and not these thickenings. So there's some underlying V-sheaf. But then you also have, and this is enough information to give you a tangent bundle. So that's sort of the point of this sort of coproduct condition, is this gives you, you can define the tangent bundle of S by just sending some thickened Fargue-Fontaine curve, say that 5 times fast, X to S evaluated on X, I'll write X sort of bracket epsilon. So that just means I sort of take my A to be the dual numbers. So I just add an epsilon that squares to 0 to the structure sheaf. I can evaluate on that. Right, and sort of in, just like sort of in, like Schlesinger's deformation theory, like this sort of coproduct rule gives you a abelian group law on this tangent bundle, and you get sort of a natural sort of QP vector space structure too, sort of coming from thinking about like what are the endomorphisms of this object x bracket epsilon over x. So you get sort of some, and in fact it's sort of like the analog of like QPLA in this setting that sort of this is a module over. So good, so you get sort of tangent spaces for these things. And then sort of the nice thing is that, oh, I can use these boards too. Okay, so that's the nice thing is every moduli problem in sort of Fargue-Scholze is defined using Fargue-Fontaine curves. So like, for example, like these moduli have modifications and Newton strata and so on. And so if all of your moduli problems are defined using Fargue-Fontaine curves, you know basically immediately how to extend them to functors on thickened Fargue-Fontaine curves. And then you can sort of just like, but now you have something where you can actually try and compute the tangent bundle. And so then also all of the computations sort of fall out from that. Good, so this sort of gives you sort of a way you can sort of linearize the theory of sort of all these moduli spaces in this geometrization program. But you can do sort of more with it. I mean, sort of gives sort of a common world with these plus like many perfectoid spaces. So I should just say with these plus many other perfectoid spaces that sort of have natural, like, most times you run into a perfectoid space, like, well, the perfectoid space is definitely not enough to tell you, like, how to give you an inscribed structure on it, but usually you built it some way. And for example, like, often you've built it out of rigid analytic geometry somehow. And if you built it out of rigid analytic geometry, then so I described many settings in this paper where then it actually has a natural inscribed structure. But also sort of like rigid analytic varieties. So like in these examples, I mean, somehow, of course, I also want sort of rigid analytic varieties to live in this world because I want to be able to get, like, when I just have like the CP, I want to be able to get that in my tangent spaces, and then you do. And then sort of, but then maybe the power of the theory is sort of combines sort of all these different things and lets you make sort of like these sort of, in the end, sort of simple computations that sort of feel like differential topology, differential geometry computations with them. Good. So maybe to connect to one other thing that was mentioned today. I mean, so for example, like Mingjia mentioned, you have this fiber product diagram, sort of expressing sort of like a diamond Shimura variety as a fiber product of like an Iguza stack and sort of flag variety along the Hecke correspondence. And you can use that same diagram, and if you want to sort of get an inscribed infinite level Shimura variety, well, then you just have to just inscribe each piece of that diagram. This is essentially an idea of Scholze, I think, in analytic precipitation, and then I sort of just adapted it here. But it's sort of easy to describe the pieces. So it's like the flag variety that shows up, like that's a rigid analytic variety. There's sort of a simple way to do that. And then you have to, the Hecke correspondence sort of inscribes via Boviel-Laszlo gluing again. And then the Iguza stack, I mean, somehow like it's not supposed to have differential structure, so you just leave it alone. You sort of give it the trivial inscription. And then you sort of form that thing, and like this gives you now you think of a Shimura variety as sort of like a p-adic Lie group torsor over a rigid analytic variety. Like now it really gives you something that behaves like that differentially. Sort of like you get something whose like tangent space is like an extension, the tangent space of like the CP tangent space of the Shimura variety at finite level by sort of this by sort of like the QP vector space that's the tangent space of the p-adic Lie group, and it ends up being sort of non-trivial, a completely non-trivial extension in that case. And in fact, you can sort of do all of that sort of for any p-adic Lie group torsor over any rigid analytic variety over a p-adic field. So in this paper that I mentioned, I sort of introduced this functor. I'll just erase this. So I introduced this functor that sort of goes from QP local systems to these things called inscribed twistors on sort of like these relative thickened Fargue-Fontaine curves. And I used it to sort of give this like some inscribed structure on any p-adic Lie group torsor, at least when you're working for a p-adic field. And also like in the de Rham case, so like sort of there's an inscribed version like the Hodge tape period mapping, like it's lattice lift, and then you can compute the differentials of these things and sort of start using that to understand sort of the geometry sort of linearized somehow. And so I did this using sort of this Riemann-Hilbert correspondence of Liu Zhu, and sort of like you had to sort of just had to reinterpret sort of one direction of their functor. But once you sort of reinterpret one direction of their functor, it sort of naturally extends to a functor, to something you can use sort of to also sort of do this inscribed structure. And in fact, I mean, so like there have been advances sort of since then. So I can't remember, I should have written down the author names, but there's two really nice papers have been written on the sort of Riemann-Hilbert correspondence in the sense of Liu Zhu. Since then, like sort of first extending it to a nilpotent one when you sort of just work over CP but have a B plus de Rham, a lift to B plus de Rham, and you can use that to extend this partially. There's also sort of a local version that you can use this to extend, and I think essentially to anything. But in the last 2 minutes, let me sort of say instead sort of how you should get this from analytic prismatization, I think. Maybe it's good that I sort of only left myself 2 minutes. But like if you have such a thickening X, and so when you sort of like have sort of, okay, like sort of S is the original analytic variety. So let's say this X, maybe my variety is going to be over CP, and then sort of this sort of this thickening of sort of some XP flat, but really sort of I have also an untilt to spot CP. So somehow this whole thing lies over the Fargue-Fontaine curve for CP flat. And so if S is a rigid variety over CP, then like when I sort of do this inscribed version of S to evaluate it on X, well, I just sort of take the maps over CP from the pullback of, so right, infinity is sort of this canonical point. So you guys have some canonical Cartier divisor in X, well, in the Fargue-Fontaine curve, but then also in this thickening. You can sort of pull back, so you can sort of, right? This is that Cartier divisor, and that so lives over CP, and you can map it to S. Okay, so that's sort of a formula you've seen before, because this is the same kind of formula that showed up in this cone construction. That was sort of one sort of corner of this analytic prismatization fiber product. Good, so you have this, and then, okay, but now I can sort of think of this X. I mean, the reason I work with like these very simple X's is because I can just think of them as adic spaces, and somehow like, moreover, like, and the reason I'm up here talking and not someone else is because, like, in particular, they're flat over sort of the Fargue-Fontaine curve. So when I take this pullback, like this is just actually like I don't need to do anything to derive. So in the big thing, like in this prismatization talks, where somehow like this pullback needed to be derived, and that's sort of where all the structure was. But somehow here, like you don't get anything. There's nothing added by sort of saying derived here. It's a flat thing, so its pullback is just really its pullback. You can work classically. But nonetheless, I could sort of still think of this thing as being a Gelfand stack over. Is it okay if I take 2 minutes? Sorry. Okay. So, but then if I ask again for okay. But I'll only ask for 1 minute that time. I'll sort of then 30 seconds then. Okay, so I have this like this Gelfand stack over sort of XCP flat, sort of viewed as a Gelfand stack. And then now I actually claim sort of like if I give, so given this, and this gives a map from this Gelfand stack version of X, my thickening, to the analytic prismatization of S, but sort of, and so not sort of the absolute version, but sort of like a relative version that I don't think was defined in the talks, but it's okay, exists. It's just sort of to accommodate sort of like something like having a rigid variety over CP. You sort of need this. Okay, so you get this map, and somehow Y. Well, like here's sort of X. Then when I sort of take this like Gelfand stack, well, I would have sort of some. So okay, so here's some n nil perfectoid, and so I would sort of test sort of my X, like so the nil perfectoid sort of over like XCP flat, and sort of it's kind of have to look like this a little bit, and then you sort of test, like you test your Gelfand stack by sort of taking these maps, but okay, and so maybe this map sort of like comes in like right here or something, but then like this extends, of course, like to a map from sort of this. So my x's are supposed to be ff's. Sorry, my xc plat. Sorry, I tried to change this everywhere, but then I screwed up. I was trying to use ff for Fargue-Fontaine curve. If I wrote just a Roman x, it means Fargue-Fontaine curve. So I have right. So I have this nil perfectoid mapping in, but then I can sort of take the Fargue-Fontaine curve for this nil perfectoid, which sort of just looks like I sort of like fill this in here, and I'm sort of able to fill this into a map from that guy. And so when I test with nil perfectoids, I also, because I sort of already have a Fargue-Fontaine curve sort of living in here, I can sort of extend this to a map from this Fargue-Fontaine curve for my nil perfectoid. But now, sort of when I test the analytic prismatization on this guy, I just taking a map from the restriction at infinity to this. So in this thickening may not be at the same point as infinity. Like this can be sort of anywhere on the curve. But I mean, like, of course, that map, when I sort of test with S, by sort of I'm going to compose with this map to get my map to I'm going to compose with this map to get my map to S. Okay, and so I just get I get my map to the analytic prismatization this way. So here's the main thing, though. Somehow, if you think about like what this depends on, so here's your x again, your curly x. Inside of here, you sort of have like, okay, you sort of have this point infinity, you sort of have the part up there. And really, somehow, if you take sort of two maps from nil perfectoids into the Scholze stack that agree sort of on restriction to this sublocus, then they give you the same map to the analytic prismatization. So what that means is sort of this, so this factors, so it's like the map you get from x to, from x Scholze to the analytic prismatization, this factors through the sort of T to ROM stack of x Scholze. So this T to ROM stack, I mean, so like you're just saying like when can you integrate sort of T connections? So T here is sort of like the sort of function that vanishes sort of at sort of the point infinity. The T connection is sort of, well, you almost have a connection, but instead you sort of have, when you delete this point, you have the connection on the outside and just has sort of like a simple pole in infinity. And anyway, sort of saying like this condition about agreeing, like only really depending on this data, that's exactly saying you can integrate a T connection. So this is sort of like morally what this means. And sort of this T to ROM stack, I mean, this is sort of a thing sort of where vector bundles on it are T connections, and or another way you say that is, and that's basically what I meant by twister. Right, so now sort of if you have a local system, you should get sort of some, on S, you should get some vector bundle on the analytic to ROM stack, and then when you pull it back to one of these guys, you get sort of this T connection, and that should be sort of this twister bundle. And this is not how I do it in my paper, but this is probably how it should be done sort of in the end. So sorry for going over, let me stop.